Okay. Um, Welcome everyone. We are going to go over some biostatistics kind of fundamentals before we dive into the subsequent videos covering specific topics on the different aspects of biostats. Now, the first thing to kind of know and to emphasize is that biostatistics is basically the study of data and the more human counterpart, diseases and how they affect people and how it can inform kind of clinical decision making. It's really applicable in terms of drug studies, about population studies, and so many things. It is essentially, at the end of the day, a variation or a very unique component of statistics. Now, there's three aspects that we should always keep in mind when we're going through this. One is that the study design is the essential beginning of where we get our data, right? This will inform us of how the data can be manipulated or studied and eventually sliced and diced in order for us to interpret the data. Now, the study design involves several different components and several different types of study designs. One, there's cross-sectional, there's cohort, there's case controlled, and then there's RCTs. Now, these are going to be covered later on. And when we move into evaluation of the study, which is basically when we get the data, how can we slice and dice the data and to find out whether if it has a correlatory properties or if there's any significance or any sort of things, we need to emphasize how this data that we just generated can be essentially broken down. So that's why we take our data and we see if there's a type 1 or type 2 errors, how we feel in terms of confidence with the data that we've received, what kind of assumptions or parameters we can work off of, such as like what you would see with your two sample t-test, your ANOVAs, your chi-square test, and also at the same time address any confounding or biases in our study so that we have the integrity of the scientific method when we're going through this. And then finally, how do we apply the said study to a population? What is the interpretation that we're trying to get at the end of the day? So this is where we start looking at sensitivity, specificity, positive predictor values versus negative predictor values, likelihood ratios, incidences, prevalences, diseases, and exposures. There's so many different things that we can eventually do with the data that we receive. But before we get into all of the nitty-gritty of all of these things, we need to understand some of the core principles of biostatistics. That's what I'm going to quickly go over today. Now, the first thing I think something that we've seen plenty of is mean, median, mode, and of course, when we finally get to talking about the data, normal distribution. Now, mean is talking about the average of all the data. And I'm going to run under the assumption that everyone knows how to calculate the average. So I'm not going to spend time going over that. The median is exactly if you take all this data and you sort it and you put it to largest to smallest or smallest to largest, where does the middle of our data sit? And then finally, mode, I like to think mode equaling most is the most common. What is the most reoccurring set of data or numbers in our data that we've collected? Like, where does it all lie in the grand scheme of things? Now, the most common thing that we often hear about, and especially going through this material, is normal distribution. Now, this normal distribution or Gaussian distribution, there are several different types of terms for it, is a distribution where the mean, median, and mode all equal one thing, right? And that's the center of our data. That's where the bulk of our data exists. Now, that is the most common form. Yet, in the real world, none of our data ever look that clean. Now, first thing we need to realize is that you can have data that has a negative shift or basically left shifted in this case. Now, what does that tell us? It tells us that our mean, median, mode aren't all equal to one another. So what happens essentially is our mean is furthest or the closest to the tail. So this will be our mean. This will be our median. And then finally, this would be our mode. And this makes sense if we take a step back and we look at it. Now, this is a left shift because we're talking about a tail. So left shifted curve based off of the tail. So the tail is basically the long component of the graph, and it's often not really, tested upon, but essentially it's important to know because it tells us how our data essentially lies in the grand scheme of things. So mean, median, and mode are very unique in the negative shift or the left shifted. And obviously, we have like another running joke. It's like if you really want to do well on an exam, you want to have a negative shift. You want the bulk of the class to be in the negative shift. You don't want them to be the normal distribution because some have done really amazingly and some have done so poorly. So and then of course in the middle sits the meat of all of the folks who took the exam. The positive shift, on the other hand, has a slightly different tail. So this tail is right shifted. Now, essentially, this changes our mode, right? Our mode is now here. Our median is around here, and our mean is right here. So that tells us that the mode relatively stays where the meat of the data is, whereas the median gets shifted slightly because of the fact that our middle of our data has changed significantly as compared to the normal distribution. And then finally, of course, the mean is changed based off of how the data is skewed. So this is essentially why we need to be kind of cognizant of how our distribution curves exist and what it really means for our mean, median, and mode, right? At the end of the day, mode is still always going to be the same thing because it is the most number of values. Mean and median are going to change, and they're going to change relatively in the same order that you're seeing on screen. So they're always going to typically either follow mean, median, mode, right? Mean being the least, median being in the middle, and then mode being the most in terms of value. And that's specifically for a negative shift, okay? And then for our right shifted or positive shifted curves, that is going to be mode being the most, as always. Median is going to be sitting right in the middle. And of course, the mean is going to predominate here. Okay, so that's essentially what you need to take away from our right shifted, left shifted curves versus normal distribution. Okay. Now, one final thing I wanted to kind of quickly address before we do a practice is variance. Now, there's a little bit of confusion when folks get confused between variance and standard deviation. Variance starts talking about your individual data points, right? Let's say you took a whole bunch of data and you start plotting it all in a graph. How much of the data or how many points away is the data from the mean, right? From the average of your data. And that tells you on an individual level variance, right? If it's 2 away, if it's -2 away, if it's below the mean. So you can start playing with the numbers and interpreting how you see and visualize the data based off of variance. Whereas standard deviation tells you for the bulk of the data, right? It tells you how far away someone is from the center based off of the mean and the actual standard deviations. So we'll go over that in a bit. But first, let's do a quick practice going over this, which is, if my iPad would cooperate, is a study is performed in a family medicine clinic in which hemoglobin A1C is measured and is in otherwise healthy males between the ages of 20 to 30. Hemoglobin A1C results range from 4% to 5%. However, an unusual number of new patients that have come to the clinic have a hemoglobin A1C of 2 to 3%, right? How would this change your median and mode? Okay, so let's take a kind of a look of our graph. So I've gone ahead and plotted our typical numbers that they gave us right here. And those typical numbers are right here, right? That's 4 to 5% is the typical kind of distribution. This is a normal distribution. Now they're saying, you got new patients and now the values now you have a bunch of new patients who are now existing in the ballpark of 2 to 3. So based off of that, more patients are going to be added here. So let's take a look at this with a different color. So what's going to happen to our curve? Our curve, as more patients get added here, it's going to start having a shift this way. And this shift is called what? It's a negative shift, right? Or the tail of our data is now moving this way. So based off of that, you can now automatically start interpreting the data. You don't even need to do any full-fledged math because as you add more people, you can imagine our slope slightly, starts turning towards this side. Obviously, your bulk of your data is always going to be in the mode, right? So that's right here. That's the mode, right? Your median is going to be the next best option, right? It's going to be to the left, right? As we're moving through. And then finally, you have your mean. So based off of this, without any full-fledged calculation, you've now interpreted this data to be mode, median, and mean. Okay, that's just a quick and easy way of interpreting this. Obviously, we won't have to do this exact kind of process for exam purposes, but we just need to have a general understanding of how the mean, median, and mode essentially change with a negative shift versus positive shift. Okay, So that's important to know. Now, let's make our way through the next tricky, somewhat tricky concept that often kind of gets sprung up on us. It's standard deviation. Okay. Now, standard deviation is essentially taking the bulk of our data and finding out how much from that bulk our data has moved, right? At any given point, if a patient is 2 standard deviations away, 1 standard deviation away, you can get a lot, right? If you can have just a rough ballpark of where the patient is on the graph based off of just this value. So to be precise, standard deviation measures the variability compared to the mean within a study/data set. Now, this is different than variability because variability is talking about the exact, precise, unique data point. Standard deviation looks at the entire set, okay? So unique for variability, the unique individual one versus standard deviation, it looks at the whole set. Now, important to note is that the typical kind of standard deviation values that we see is that 1 standard deviation is 68% of the data, right? 2 standard deviation is roughly 2 or 1.96, and that's equivalent to 95% of the bulk of our data. And then eventually 3 standard deviation, to be technical, 2.58 is equal to 99%. Essentially, at that point, we're saying 100% of our data is being taken into account with our standard deviation process. This is important to note because standard deviation tells you how much of the data you can't account for, right? How much of the value you can't really factor into your analysis with the deviations, right? From the mean, how far the data is. So 32% for 68, right, falls outside. Now for the 95, 5% fall outside. Okay. And then finally, for the 99% or essentially 100, it's almost 1% fall outside. And you can, and when I say fall outside, we're talking about both sides of a typical bell curve, right? Or normal distribution curve. Okay. What we now have to look at is the calculations or the formula. And here I put the formula for standard deviation, both for the population equivalent as well as the sample equivalent. Note the slight variation here because you have n minus 1. Okay, critical to note that's the n minus 1. Everything else is essentially the same. Okay, and if you notice, what's unique between our standard deviation and our variance is that one gets squared and the other gets square rooted. It's as simple as that. So as you're going through the process of breaking down and calculating your standard deviation or variability, one way or another, you're making those tables, your graphs. It helps you see how this data gets sliced and diced and seeing where majority of our data lies. Now let's take an example. Okay, now the mean systolic blood pressure is typically 120 millimeters of mercury. Okay, now what happens when we say a standard deviation of 20 versus 5? Okay, what we're saying is you're going to have a greater kind of distribution of your data, right, of where the values essentially lie with a 20 standard deviation as compared to 5. You have a greater clustering of your data in this pocket, okay, essentially, and very less here. Whereas here you have greater variance, you have greater kind of spread of your data. And that's important to kind of note so that you have a mental representation of what they're talking about when they say a 20 versus a 5 standard deviation. Okay. Now that's important to note. And then finally, when we're going through this, you can also calculate the standard error of the mean. Okay, SEM. Now, what does that tell us? What is the point of SEM? It measures the variability between the mean of the sample and the general population. Okay. Now, in simpler words, it's telling us if I took my sample, how does it compare to the general population? Is it equivalent? Do we have a good variability, or is there very close variability? Like, it's important to denote these things, and it's critical. Now, the formula for SEM, or standard error of mean, is standard deviation over square root of n. Okay, and when we use the little n, we're talking about the sample. Okay, you can do the same process for the population and find out how they cross compare. Now, some general principles to remember for SEM, and it's not something we need to sit and calculate every day. The general principle is that as you increase your sample size, you decrease the chances of making errors. So that decreases variability. So your data becomes very similar or closer clustered to your mean. Okay. Now, obviously, when you decrease that, let's say you took a survey of folks in a classroom and you saw like, okay, I'm only going to take a survey of 2 people out of a population of 1,000. it's going to be vastly different because those two people's opinions and thoughts are going to be vastly different from the rest, right? You need a bigger sample size. So less in terms of sample size, it's going to increase your SEM and increase the variability. So your data is going to be much more dispersed from the mean of the sample and the general population. So important to understand that key principle of why most of the studies in the scientific world and literature isn't in small clusters. Typically, really major research tends to happen with large cohorts of people, and we're going to get into that in a bit. And then final concept I kind of want to address is z-scores. And this is something that's so simple that it can be confusing, is how many standard deviations from the mean is essentially the definition of a z-score. So 2 standard deviation, what's the z-score going to be? It's 2. Now, what does this essentially tell us? So why do we even have a z-score? I mean, I can just tell you the standard deviation and you should be fine, right? Not really, because a z-score, if you are a layperson or someone who wants to make a quick snapshot judgment, let's say your patient has come into the clinic and their z-score is 3. So what you automatically think is that of all the patients that have ever come to your clinic, right, they are in the highest percentile for your hemoglobin A1C. This could either be a good thing or a bad thing. So important to know that this interpretation allows us to make quick snapshot judgment and helps us inform kind of decisions, right? When we're discussing how we present the data, what we do with the data, and clinical decision making. Just a kind of a quick example. So to wrap up the concept, let's just go over an example. So a study of 200 elderly males between the ages of 80 to 89 evaluates their cognitive ability with a mini mental score assessment, right? You guys are very familiar with this. We covered in neuro. The average score turns out to be 23 out of 30. That's the possibility, with one standard deviation being 2 points, and how many patients have a score of 19 or lower. So let's kind of interpret everything that's being tossed at us, because it is important, and there's a lot of things that they've kind of explained here. 20 elderly tells you your N, right off the bat. Now, their age is given. I don't know if we need that yet, but then what we do get is the average score, which is your mean right off the bat. You don't have to think too hard for that one. And standard deviation is given. So that's 2 points for SD, right? And how many patients have a score of 19 or lower? That's what we're looking for. So now that we know all this information, let's slice and dice this thing. So I've already plotted this just for kind of time's sake. So we know that our mean is going to be at the very center, knowing that this is a normal distribution. Okay, so now we have to put our standard deviations on this plot. So 2 standard deviations above is going to be, and then we'll go 2 points above. So what are we going to have? We're going to have 25. So if we do the exact opposite, right, of the folks who are below the mean, it's going to be what? 22. Okay. And then finally, let's say folks who are the lower half, once again, right, 2 more points, or yes, 2 more points, you're going to have folks in the 20s. Okay. And then if let's stay, just for completion's sake, let's do both 68% as well as 95. So 2 standard deviations we'll do above and below. So here it's going to be 28, right? So what they're essentially asking is, what about patients that are just in this range? Okay, how many patients are going to be just in that ballpark? So based off of this, what you need to realize is the numbers we previously talked about, which are right here, right? Going over these. Right. And these will help you see how the numbers are essentially sliced and diced. So we know that the patient, or sorry, the folks that are below are 2 standard deviations. So how much of the data is 2 standard deviation that we aren't taking into account? 5. So 5, we have to divide that by both sides. So let's take a peek. So 5, divide that by 2. And what do we get? We get a brilliant number called 2.5. Okay. So on both sides, we have 2.5 and 2.5, right? But we just want to know for patients who are 19 and below, right, in terms of their MMSE score. So what do? We take this 2.5, right, and then multiply it by our sample, right? And our sample, we said, is 200. So multiply that by 200, and what do you get? You get, right, we have to convert this into fractional units so that we get a clean value, and that's going to be 0.025 multiplied by 200. And what do we get? 5 patients, right? 5 patients who are essentially below 19 in our MMSE scoring, okay, in terms of the data. So we are just looking at this tail, right? Just this tail. That is how we can slice and dice this data and understand and interpret relatively quickly as compared to resampling everyone, running all these analysis. We can get a quick snapshot understanding of everything that's going on based off of just data that has been analyzed by a biostatistician. Obviously, not every single exam is going to make you calculate all this. Just for principle's sake, I wanted to make sure everything was covered. Thank you very much, and I hope this addressed any of the confusion or questions you had about some of the fundamentals of biostatistics.